Boy, I sure love this weather. Climate. What's the difference?
This video is a beginner's guide to everything you should know in order to understand the weather.
Hey everybody, Dave here. Today we talk about weather and climate, why you should know the difference, and the factors that affect your home climate.
Now, weather is the state of the atmosphere at a specific place and time.
Sunshine. Ooh, that's quite a breeze.
Rain.
Dude, it's humid out. Snow day.
But if you wait an hour, the weather is going to change. Temperature, humidity, precipitation, cloud cover, and air pressure. The only constant is change. But climate is different.
If you have a friend moving from across the country and they want to know how to prepare, you tell them the climate, not the weather.
It's the average weather conditions for a location over a long period of time, like 30 years long. So you'd say it's dry or humid or overall hot in the summer and cold in the winter, constantly freezing, or maybe it's tropical.
Weather and climate have been in the news for, forever.
So why does the difference matter? Well, imagine someone confusing a single hot day with climate change. It's not cool. Understanding the difference is key to navigating the climate conversation intelligently.
You can't tell if climate is changing from a single day or even a single year. Climate is much bigger than that.
There are 5 key factors that influence the climate of a region.
The first, and my favorite, the rain shadow effect.
When air goes up mountains, it cools and can't hold water vapor, so clouds form and then rain falls. Then the air is dry on the other side and you find deserts. Just take a look at the Himalayan mountains in Asia. Can you tell which side the rain shadow desert's on?
I shouldn't admit this, but I always wanted to name my first kid Rain Shadow Wookner.
Second is latitude. The closer you are to the equator, the higher the sun is in the sky over the year and the stronger and more concentrated the sunlight. So you typically stay warmer year-round like in the tropics. And here's me on the summer solstice in Hawaii, grinning because the sun is directly overhead and I have no shadow. The third factor is altitude. The higher you go, the colder the air is. Think Mount Everest. This has to do with lower amounts of air or lower air pressure and the resulting lower temperature. It also explains why people look like this when skiing. Fourth is proximity to oceans, along with the direction of the wind. Typically, if you're on a coast, your temperature doesn't change much over the year. But if you're in the middle of a continent, it does. Air takes on the characteristics of its current location, so air sitting over a cool ocean is cool and full of moisture. So on the west coast of the US, where the wind is blowing in from the ocean, it keeps the temperature down in the summer and up in the winter. On the US's east coast, while you're closer to the ocean, the wind is coming from over land, so that doesn't help much. Sorry guys. But at least you're not in the middle of the US, where it's hot in the summer and cold in the winter.
And now the fifth and final factor that affects climate, ocean currents. Great Britain and Ireland absolutely blow my mind.
Do you realize that Northern Ireland and the southern Hudson Bay in Canada, where polar bears live, are at the same latitude? But Britain and Ireland are much warmer due to the Gulf Stream current that brings up warm water from the tropics.
So you put these factors together and you have your climate.
Here in Colorado, the climate is summed up like this. We're on the leeward side of the Rockies, so we're pretty dry. We're higher in elevation, so we're a little cooler. Our latitude is 40 degrees, so we're right in the middle. We're nowhere near an ocean, so we have warm summers and cool winters, and the ocean currents don't affect us like they do many other places.
Take a look at where you live, see what factors affect you the most, and let me know. I hope you have a great day.
Weather is the most complicated, simple thing on Earth, because while a million things make it hard to predict, these 2 things make it easy to understand. Hey there, curious minds, Dave here. In today's video, we talk about the why behind the weather, from air masses to wind and humidity to hurricanes. And we start with air masses. And air takes on the characteristic of the place where it's hanging out. So over the North Pacific Ocean, the air is cool from weaker sunlight and humid from evaporating ocean water. Over the deserts of northern Mexico, it's dry and hot. You get it. Take the Earth as a whole, and there is an array of what are called air masses blanketing the planet. Each one with a uniform temperature and moisture content. Pair a moisture content with a temperature, and you have yourself an air mass. For example, if it's dry and cool, we call that continental polar, and if it's warm and humid, it's maritime tropical. Just calling it dry and cool would be boring, so scientists decided to spice it up a little bit with some new vocab. And these air masses hitch a ride with the second thing you need in order to understand the weather: global winds. Not the local ones you feel outside, but the real deal, high up in the atmosphere. Let's start here at the equator, where it's always warm and the air is always rising. But when the air leaves, there isn't a vacuum of no air with people trying to catch their breath. Air from just north or south of the equator flows into the region to fill in the gap. Like this aquarium, if I pull a bunch of water up from the middle, it doesn't leave an empty space where the container was. Water flows in from the sides to even it all out. But to make it interesting, when the air comes down from the north or up from the south, because the Earth is rotating, something curious happens. Imagine this paper is the top half of the Earth. As the Earth rotates, I'll draw a line straight down from the North Pole. Well, that's weird. The line curved to the right. It's easier to see from this perspective. Between 30 and 60 degrees latitude, air is moving from south to north, and also curves to the right. This is called the Coriolis effect, and explains the motion of everything from tornadoes to hurricanes. And if you zoom out to look at the whole planet, you end up with 6 global wind belts of air rising and sinking at different latitudes and curving because of the Earth's rotation. So you're hanging out somewhere, and global winds bring in new air masses, and with them, new weather. Here in the United States, this brings most of our weather from the west, but sometimes it can come up from the east at lower latitudes. And this explains why, when flying from Colorado to Nebraska, the states may have different air masses and totally different weather. Colorado's air mass being cooler and dry from the west, and Nebraska's warm and humid from the Gulf of Mexico. Geographically close, but meteorologically far apart. And now the paths of a hurricane becomes clear. They form in a wind belt pushing them west, then enter the next one up that goes back east. It's not random, it's the Coriolis effect. Air masses and global winds are a dynamic duo that keep us on our toes.
But it's also important to understand that not all things you experience with weather have to do with air masses and global winds. Here in Colorado, it was 43 degrees when I woke up, and it's going to top out at 81 this afternoon. And that's primarily because of our climate, how we're really high in elevation and nowhere near an ocean. So as Mark Twain said, if you don't like the weather, just wait a few minutes.
An airplane takes from Tokyo to Denver really curve like this? And if so, why? The answer actually blew my mind just a little bit. But first, I recently left Tokyo at 4:15 on a Sunday afternoon and landed in Denver at 11:48 on a Sunday morning after traveling for 11 hours, which had me thinking, did I just break time? There are 24 time zones around our planet. Each one is about 15 degrees of longitude and width, but sometimes that changes because of geographical reasons like mountains or political reasons like boundaries of countries or states. China opted to go with 1 time zone instead of 5. Bold move. Time zones arose because Earth rotates 15 degrees every hour, and 24 hours times 15 degrees equals 360, one full rotation. So during my flight, I went forward 9 time zones in 9 hours, back 24 hours because I crossed the international date line. This took 11 hours, getting me there 4 hours ahead of the time where I started. So no, I didn't break time, it's just a little weird. Something was troubling me as I tried to sleep on my flight. If we left at 4:15 p.m. and would arrive at 11:48 a.m., what was the sun doing outside? I couldn't see out. Was it going backwards in the sky? Did it set or rise?
Now imagine a line that starts at due south. It rises up to the highest point above you, which is called your zenith, and then it continues to due north. This is called the meridian. And as the sun rises in the east and gets higher and higher in the sky, at noon it's going to reach the meridian, its highest point. We call this AM for anti-meridian. And then the sun will continue its journey as it sets over in the west, and this is post-meridian or PM.
So here's the position of Tokyo at 4:15 p.m. on the day side of Earth, and here's Denver, my destination, on the night side of Earth. During our 11-hour flight, the Earth made 1/2 rotation, and as a result, we zoomed right through the night side of Earth, landing in Denver when the sun was at its highest point on the sky, right on the meridian at noon. Now, would a plane really go from 36 degrees latitude at Japan to 52 degrees latitude over the Aleutian Islands and back to 40 degrees at Denver? It seems to me it would just make more sense to go in a straight line from point A to point B. But there's a problem with maps. They're a 2-dimensional representation of a 3-dimension sphere, and unfortunately distort our perception of Earth. To find the quickest route between Tokyo and Denver, I'm going to take a string and pull it tight so that it automatically falls along the shortest path between the two. And there you have it, the string follows the flight path almost exactly. I even measured the 2 routes using string, and it turns out the one that follows the lines of latitude was 12.2% longer. But there's another thing pilots have to take into consideration when choosing their course: wind. During World War II, Americans began finding mysterious objects like this one scattered across the countryside. Upon closer inspection, we found that they were laden with explosives. It turns out that these were Japanese balloon bombs. But how did they get here? Well, in the 1920s, a Japanese meteorologist discovered the jet stream, seen here in red. Well, balloon bombs and airplanes can both use the wind to get across the Pacific Ocean from Japan to North America. And an interesting fact, American geologists were able to pinpoint the exact beaches where these balloons launched from using evidence in the form of sand. Science is so cool. Speaking of balloons, I had this idea. If the Earth is rotating, why don't we just take balloons up into the sky, let the Earth rotate underneath, and then come back down somewhere new? Brilliant, right? $1 billion idea. Only there's one problem. As you can see, with planes and balloons going across the Pacific Ocean, the air rotates with the Earth because of friction. The ground pushes on the air molecules touching it, they push on the air molecules touching them, and pretty soon the sky is moving with us. Which makes sense. Otherwise, as the Earth rotates at hundreds of miles per hour under the atmosphere, it would be like the world's worst hurricane. So a lot is going on when you fly. There's time getting all messed up, wind is blowing, the Earth is a giant rotating sphere. It's amazing to me how man-made creations like airplanes, time zones, and science bring the world together and explain what the heck is going on.
Hey, are you guys ready for the pool yet? It's almost summertime. It's summer in the southern hemisphere? Crikey, I was way off.
Hey everybody, Dave here. Today's video is about why we have seasons here on Earth. So let's go ahead and get started by testing your seasons knowledge. Which of these 4 images most accurately shows the shape of the Earth's orbit as it goes around the sun? And the answer is C. But please don't feel bad if you get this wrong. If you Google Earth's orbit around the sun, most of what pops up is either misleading or incorrect. It turns out that the Earth's orbit is by far closest to a circle, but it's technically an ellipse. On average, we're 93 million miles from the sun. But at our closest, we're 91 million miles, called perihelion for you science geeks, whom I love. And at times, we're 95 million miles from the sun, called aphelion. Which brings me to my second question. At what time of the year is the Earth closest to the sun? Is it the first week of A, January, B, April, C, July, or D, October? And the answer is January. Confused? Don't be. It's simple. The distance between the Earth and the sun is not the cause of seasons. To hammer this fact home, if the distance was the cause of seasons, then the entire Earth would be experiencing summer at the same time, and the whole Earth would have winter at the same time. But we don't. While it's summer in the northern hemisphere, in the southern hemisphere it's winter.
And now for the amazing science questions of the day. Number 1. Which planet in our solar system has seasons most similar to Earth's? And number 2, which planet has the most extreme seasons? Stay tuned for the amazing answer.
Now let's recreate what's happening to cause seasons here at home. I'm going to model what really causes seasons using a light meter app on my phone and a globe of the Earth in my backyard. And I'll take measurements of how much light energy is hitting the Earth all the way from the equator up to the North Pole. At the equator, the light is hitting my phone directly, at a 90-degree angle. Imagine a tiny person standing on the equator. To them, the sun would be directly overhead. So that's where I'll begin. With my assistant Theo, I take a reading of light energy at the equator, then move up to the Tropic of Cancer at 23.5 degrees north latitude, up to Boise, Idaho at 45, the Arctic Circle, and finally the North Pole. Now let's take a look at the results. As we go further north, the amount of light energy goes down. At the equator, where the sun's at 90 degrees directly overhead, there's 800 lux of light energy. And at the North Pole, where the sun is on the horizon at 0 degrees, there's only 10 lux of light energy. Here's the thing though, that data was for an untilted Earth. In reality, the Earth is tilted 23.5 degrees off its vertical axis. Sometimes the northern hemisphere is tilted toward the sun, and sometimes it's tilted away from the sun. So I collected data for those scenarios as well so that we can compare our results. And here are the results. The red line on this graph represents how much light energy is hitting the Earth's surface at different latitudes when the Earth is tilted toward the sun. The blue line is when there's no tilt, and the yellow line is when the tilt is facing away from the sun. There's a huge difference. There's way more energy hitting the northern hemisphere when the Earth is tilted toward the sun, as shown on that red line. You can see that as the northern hemisphere is tilted toward the sun, sunlight is hitting the Earth at a 90-degree angle north of the equator, at the Tropic of Cancer. At the North Pole, it's hitting at a much lower angle, about 23.5 degrees, but it never goes onto the night side of Earth, giving it 24-hour-long days. We in North America also get much longer days, as we are on the day side of the Earth much longer. When the tilt of the Earth is leaning away from the sun in the northern hemisphere, sunlight is hitting the southern hemisphere at a 90-degree angle, and they are having much longer days. It's summertime in January. But the North Pole, it doesn't even reach the day side of Earth, and North America has a very low angle of light, and quite weak. And light striking a surface at 90 degrees and being so incredibly strong explains a lot of things you see in your daily life, like why you're so fast to sunburn on your shoulders and the tops of your ears, why people place solar panels facing the direction they do to generate electricity, why ski resorts are typically found on the north sides of mountains when the sun is in the south. So to summarize, seasons are not the result of the distance between the Earth and the sun. The tilt of the Earth results in the sun being higher in the summer and lower in the sky in the winter. It also changes the length of days for those time periods as well, which in combination give us our different seasons. So there you have it. The mystery of the seasons has been solved.
And the answer to the science questions of the day, first one anyway, is Mars. Mars has a tilt very similar to Earth's and therefore has seasons really similar to Earth's as well. In Mars' summer, you could almost even live there. And the answer to the most extreme seasons on Earth is Uranus. Uranus' tilt is at 90 degrees. It rolls along in its orbit as it goes around the sun. It's pretty crazy and extreme.
I hope you enjoyed this video, and if so, please like, subscribe, and leave a comment. Have a great season, wherever you are, in whichever one it is.
No, trees. I need oxygen.
If there are no trees in the desert, how is there oxygen to breathe?
False alarm. Good. Today's video is all about oxygen, why we need it, where it comes from, why it's one of the most important things on Earth, and how littering can leave us all breathless.
Let's start with the question of why in places with no trees do you still have oxygen to breathe? You can think of oxygen like a silent and smelly fart. You know it started at one point, but pretty soon it's everywhere. This is called diffusion, where high concentrations of a substance like oxygen spread out more and more until the concentration is low. All liquids and gases do it. Plus, air is never really still. Global winds are pushing air masses all over the planet, so the air over the desert, it didn't start there, and it certainly isn't just hanging out. So where does oxygen actually come from?
Oxygen comes from the process of photosynthesis. Wait, it's not boring, it's actually pretty cool.
I'll keep it simple. Plants, algae, and phytoplankton, basically anything with chloroplasts in their cells, create their own food in the process of photosynthesis. That's right, just like people, plants need food for energy. They take water, carbon dioxide gas, sunlight, and rearrange it into sugar and oxygen.
Clever little things. The sugar they use as food. The oxygen, they don't. So they let it go free. Some people refer to oxygen as plant poop. Wait, nobody calls it that? Just me?
So where is most oxygen made? If you're thinking a rainforest, that's a great guess, but no. Earth is a water planet, and while rainforests are incredibly important, oceans are where most of the oxygen is made. 75% of the Earth's oxygen is made in the oceans by kelp and phytoplankton, and 25% is made by plants on land.
So healthy oceans are an absolute must-have for life on Earth, which is why you should never litter.
Because trash on the ground always makes its way to a stream, and streams flow to rivers, and the rivers, they end in the oceans. You see, everything on Earth is connected. So what exactly is oxygen? Oxygen is an atom that looks something like this, and atoms are incredibly small. There are 94 different types of atoms found naturally on Earth, seen here on the periodic table, but oxygen is by far the best. But before I explain why, do you know which of these we breathe in order to live? Is it a single oxygen atom known simply as O, two oxygen atoms known as the molecule O2, O3, or O4?
It's not O1, that doesn't exist in nature, and it's not O3, that's complicated.
The answer is O2, floating in the air or dissolved in the water that fuels life on Earth. It's a molecule where two oxygens are bonded together and happy. And O3 is called ozone. It comes from pollution and is toxic for us to breathe, but it is found naturally in the atmosphere and blocks ultraviolet radiation from the sun, and is the only reason we can live on the surface of the Earth and aren't hiding from the sun in caves.
In O4, some say it's a secret government creation that gives its breathers extra special mind control, strength, and physical abilities. Just kidding, I made that up. There's no O4 in nature.
Which leads me to my top 3 reasons why oxygen is the best. Number 1, we need oxygen to live. The cells of our body use oxygen in a process called cellular respiration, which releases stored energy to power our body and brain. And 2, as ozone, it allows for life on the surface of the Earth. And 3, it's a key ingredient in water, 2 hydrogens and an oxygen, another vital substance for all life on Earth. And water without the oxygen is just H2, which you can't drink because it's a combustible gas.
I could go on all day, but I won't. I'll stop there.
To summarize, oxygen rules. It's found everywhere due to diffusion and the movement of air. Phytoplankton in the ocean are the real all-stars of oxygen production, but all plants play a vital role, so we want to keep our planet clean and healthy. We breathe O2 oxygen molecules, but ozone keeps the surface free of harmful UV radiation from the sun, and combinations of different types of atoms give us different products that are vital to life on Earth.
I hope you found this video a breath of fresh air. If so, like, subscribe, and comment.
California is notoriously susceptible to fires. This video can explain wildfires anywhere in the world, because all fires require 3 things to thrive. Number 1 is fuel. Fire is a chemical reaction between oxygen in the air and a fuel source that would like to react with said oxygen. The natural chaparral scrubland communities of Southern California are in a way the perfect fuel source. The leaves of these plants are often high in oil content, a fuel, and they are almost always dried out and ready to burn. Because though places like San Diego and Los Angeles may look green and lush in the city limits, outside of the downtown areas and suburbs you have homes and subdivisions abutting canyons of desert shrublands. And these canyons and open areas are oftentimes very windy because as wind flows through a constrained area, it speeds up, like river rapids in a canyon. Which brings us to the next thing fires need to thrive: oxygen. If you've ever made your own fire, you know blowing on the embers and allowing air into the base is critical to getting it started. Not only does Southern California have canyons that speed and concentrate wind, they occasionally have their famous Santa Ana winds. These winds are a staple of Southern California when high-pressure systems east of the major cities have cool, dry air descending from higher in the atmosphere. When the air nears the ground, it spreads out towards areas of low pressure, often over the ocean. And these winds not only supply the oxygen the fire needs to burn, but they carry embers ready to start fires on any fuel source at speeds of up to 75 miles per hour. People can often be caught off guards with the speed and intensity of the fires. So right now there is an abundance of fuel and oxygen in the greater Los Angeles area, and all that was needed was the third part of the thriving fires: the spark that begins it all, which can come from anywhere: lightning, a cigarette, a hastily put out campfire, anywhere, which is why it is so incredibly important to pay attention to your actions in a time of wind and abundant fuel. And a special thank you to the firefighters and all the others who put their lives on the line to protect people and their communities. What's the deal with the heat index and the dew point? Can it really be 100 degrees and 100% humidity? And can Antarctica really be a desert? And why and where do clouds form, and is that different than fog? Well, in today's video, we answer these questions and more, calculate how much moisture is in the air, and then I'll show you how to make clouds in a bottle and see how it's all related to one commonly misunderstood thing: relative humidity.
If we could find the mass of the air inside this cube, it would be about 1 kilogram or 2.2 pounds. And do you know how much water I could evaporate into this cube of air before the air was totally saturated and could hold no more water vapor? Is it 14 grams? A half a gram? Or is it closer to 50 grams? The answer, well, that's where humidity gets interesting, because it's all relative.
At 70 degrees Fahrenheit, a kilogram of air can hold 14 grams of water vapor. So when I have 14 grams in it, that is 100% relative humidity.
And if the air can hold 14 grams of water vapor, but I only evaporated 7 grams into it, that's only holding half of what it could. That's 50% humidity. The air's just not living up to its full potential.
But what if it's like -10 degrees? You know, Antarctic cold. Well, that kilogram of air could only hold about a half a gram of water vapor before it was saturated in 100% humidity. So 100% humidity in Antarctica is far drier than 100% humidity somewhere with 70-degree air. And that also explains why Antarctica is technically a desert. It's just too cold to even hold moisture in the air to precipitate.
But what about summertime in Florida, which I'm not gonna lie, sounds kind of nice right now.
If it were 100 degrees there, could the humidity be 100%? Well, 100-degree air can theoretically hold close to 50 grams of evaporated water, but that almost never happens. Even being just 70% humidity at 100 degrees is really, really humid. It would have 35 grams of water vapor in a cube of air. That's over 2 times as much as 100% humidity at 70 degrees. Enough to get people telling stories when they come home from vacation. I'm sure it felt like it must be 100% humidity, but it was probably just hyperbole.
And this brings me to the heat index, another common addition to weather forecasts and directly related to relative humidity.
You see, humans cool down by sweating, where our body heat leaves with the evaporating sweat.
And in really humid air, less evaporation happens.
In fact, if the humidity is 100%, evaporation pretty much stops and things just don't dry. Because at this point the air is like a sponge full of water that can't hold any more. And if there's no evaporation, then you can't cool down. And the same goes for your dog, who cools down with evaporating saliva while it pants.
And because of this, we have the heat index, which is what the weather feels like instead of what it actually is.
Here's the heat index chart. At 100 degrees, even 65% humidity feels like 136 degrees. It's miserable. The chart doesn't even go to 100% humidity at this temperature because it doesn't happen. It would feel like you were on Venus. Now, before I move on to all the other fascinating stuff that has to do with relative humidity, if you ever want to calculate your own relative humidity, whether out of curiosity or a severe distrust in the weather establishment, all you need are 2 analog thermometers, room temperature water, a small piece of paper towel, some mildly strong shoulder muscles, and something to fan with. Start by dipping a piece of paper towel in the water. Now wrap that piece of paper towel all the way around one of the bulbs of the thermometers. Keep the other thermometer dry. Then you can start fanning until the temperature of the thermometers stop changing, and record the temperature change of both. Then use this chart. When my kids did this, my dry thermometer was 70 degrees, the wet one dropped about 15 degrees, and on the chart that falls right at 36% humidity. Nice job!
And remember, if the humidity were 100%, there'd be no evaporation and no drop in temperature. So the more that temperature drops, the less humid it is.
Thanks guys, now go get the neighbor's humidity.
Now, I'm excited about the next part of this video because this is something that not everybody knows about, but they probably should. It's the dew point. And the dew point is the gateway to understanding humidity, clouds, precipitation, fog, dew.
Let's say it's 50% humidity right now, and the temperature of the air is 70 degrees. A kilogram of air would have 7 grams of water vapor in it, but it can still hold 7 grams more. But what happens if the temperature begins to drop? So does the maximum amount of the water vapor that the air can hold. And here, something happens, because at 50 degrees, the air can only hold 7 grams of water vapor, and that's what's in it. You have reached the dew point, the temperature that the air can no longer hold all of the water vapor in it, and the relative humidity is 100%. So what becomes of this water vapor? Well, it begins to condense and turn back into a liquid. If the air reaches the dew point in the sky, that's where clouds begin to form. If this happens on the ground, we get fog. Or if the air is touching something colder than the dew point, water vapor condenses onto that thing, like a glass of cold water or grass. And if the dew point is below freezing, it condenses straight into frost. Understanding relative humidity and its sibling dew point explains a lot of the things we see and experience. We even use it to forecast rain or snow, because guess what happens when the temperature keeps dropping past the dew point? That's right, precipitation. Now for a quick segment I like to call Nature Makes Beautiful Clouds, So Why Can't I? Well, you can. You can do it by taking a hot shower, or opening up the dishwasher mid-cycle, or breathing outside on a cold day. See the warm, moist air quickly cooling down past the dew point? Or you can make a cloud in a bottle at home by doing the following.
If you've ever wanted to make a cloud, it's actually really easy. All you need is a plastic bottle, hot water, and some matches. And here's how you do it. Start by putting the hot water in the bottle, maybe about an inch or so into the bottom. Then you seal it up really fast so you don't lose that hot air full of water vapor. The next step is you get a match, light it, and then blow it out inside the bottle so that some smoke goes in there.
The smoke acts as what's called a condensation nuclei. It gives something for the water vapor to condense out onto when it forms into a cloud. The final step is that you need to get the air in this bottle to go down a little bit in temperature, which might seem hard, but it's pretty easy because all you have to do is this. You squeeze to increase the pressure in the bottle and increase the temperature, and then you release to decrease the temperature and pressure inside the bottle, and there you have a cloud in the bottle. Once again, you squeeze and release, and you have your cloud in the bottle. What happens is the temperature of the air decreases below the dew point temperature. The air can no longer hold all the water vapor inside of it, so it condenses out into little tiny droplets on the smoke particles that are floating invisibly in there. There's your cloud. Philo cloud.
What do crows, crocuses, crayfish, crabapples, and my brother Craig all have in common? Well, they all need water to live, and so do you and I. And so the question is, where is all the water in the world? And more importantly, why should we care?
When we look at Earth from space, it's pretty clear that it's a water world. Around 70% of the Earth's surface is covered in water, while the other 30%, it's land.
But if we focus on the water alone, ignoring the land, we may see something surprising. 97% of all of the water in the world is found in the oceans.
To help us see just how much that is, out of these 100 squares, 97 of them are ocean water. That's a lot, and it is salty, which is great if you're a shark, salmon, sunfish, sea star, sea sponge, surfer, or sailing on a yacht.
For the rest of us animals and plants on the earth, it's not much help. We can't drink it, water our plants with it. We can't do much of anything.
If you've ever been to the beach and been pummeled by a wave, you know exactly what I'm talking about. Ocean water is just too salty. Our bodies can't handle it.
Now let's do the math. If 97% of the water in the world is found in the ocean, that leaves just 3% found on the rest of the world. Now that water is mostly fresh water,
The kind you, me, and the trees need to survive.
and it's found in 4 more places or categories, which we'll add to our chart now. In the second most common place to find water on the earth, coming in at around 2% of the total amount of water, is found frozen in ice caps, glaciers, and snowy mountains.
And while breathtakingly beautiful, unfortunately it's not much use to us because it's frozen. And no, we can't go melt it and put it in bottles or tow icebergs down from the North Pole. It's too expensive, too difficult, needs too much energy. So it's mostly as useless as ocean water.
Fun fact, if you were to melt the Alps Glacier in Switzerland, you would be able to provide every person on Earth with 1 liter of water every day for 4.5 years.
Thanks, sweetie. Okay, 97% in the oceans, 2% frozen. That leaves just 1 empty square on our chart. Which brings us to the next place you find water on Earth. Underground. It's called groundwater.
This is around 0.6% of all the water on the Earth, a little over half of a single box on my chart. We do have wells in the Earth that pump it up, but it's literally inside of rocks, not in big caverns with lakes at the bottom. And while useful to some people, most of it's impossible to get.
Looking at our chart, we find that we're almost out of space, and we still haven't found any of the really useful water. Where's all the good stuff? Next is the 4th category, and my personal favorite.
Surface water, like lakes, ponds, rivers, and streams, finally something we can use. But this water accounts for just about 0.02% of the water on Earth, a mere speck on our chart. That's it. That's what most life on the surface of Earth depends on for survival.
How's that even possible? Don't we need more water than that?
Good question. It is a bit surprising, isn't it?
But humans are resourceful, and we've found ways to make a little go a long way.
And finally, the last place on Earth where you find water is it's the last category, the 5th and final place. There's not much water there. Ah, man. But sometimes, numbers don't mean much unless you see them represented by something real. So let's take a look at this one more way.
Now imagine this 5-gallon tank had all the water in the world shrunk down to fit inside. How much would each category of water be compared to that? Well, this ice cube represents the frozen water of the world and is 5.5 tablespoons of frozen water, 2% of that starting 5 gallons. And this beaker contains 1.7 tablespoons of water, representing the groundwater, or 0.6% of the world's water, soaking into the sandstone. And this single drop of water on the leaf is 0.12 tablespoons of water, or 0.02% of the water on Earth, the surface water, representing almost everything that sustains life on the surface of the planet. Which leaves our tank still holding 97% of the Earth's water. Beautiful, salt-filled ocean water.
And the little itty-bitty amount of water in the air, well, it doesn't even show up. As you can see, those of us who dwell in the non-ocean part of the world, we rely heavily on a scarce resource. And if you leave this video with just one understanding, it should be this.
We have to be good to our water. We need it a lot more than it needs us. What do you see when you look at the clouds? Have you ever wished that you could fly through them and wondered what would be there if you did? Today you'll learn everything you never knew you wanted to know about clouds. How they form, what they are, how they affect the Earth, what are their names, and how to make one in a bottle. Now what are we seeing here? This is not water vapor. These are tiny droplets of water, tons of them, so close together you see it as a cloud.
So there's water vapor in there too, but you can't see it because water vapor is an invisible gas. The only way we know it's there is that sometimes when air touches cold objects, the water vapor will condense out of it onto those cold objects, like dew on grass or beads of water on the side of a cold glass. So clouds are just enormous amounts of itty-bitty tiny drops of water, so small that they float through the air like motes of dust on a sunbeam.
If you sit and watch clouds for a while, you start to notice their ephemeral nature. They come and go as they please, showing up out of nowhere, then disappearing just as quickly. Or sometimes, the clouds just won't leave at all, and they can bring you down.
Now clouds aren't indecisive or mean, they're just sensitive. They need things, kind of like humans. Metaphorically, not literally. And here are the 3 things that clouds need in order to form.
Number 1, the air they're in has to be holding all of the water vapor that it can. We call this being saturated or 100% relative humidity. It's like a sponge that can't hold any more water. Number 2, the air has to have condensation nuclei. Dirt, dust, salt, smoke, any tiny floating thing that the water vapor can't condense onto.
Absolutely clean air means absolutely no clouds.
And number 3, the air's temperature needs to cool, because the cooler the air, the less water vapor it will hold. You can see this at the top of mountains. When warm air full of water vapor goes up, it cools at higher elevations and condenses to turn into a cloud.
Check out the tutorial at the end of the video to see how you can make a cloud at home. And clouds do a number of things that make them incredibly important for the planet and for people.
They contain water that all living things on Earth rely upon for survival. It comes down as rain, snow, and other forms of precipitation. And during the day they reflect sunlight back into space, cooling us off. But at night the clouds trap infrared light or heat, keeping it warmer. They're basically nature's blanket. They also make sunsets even that much prettier.
To start identifying clouds, the first thing you need to do is figure out what form or shape they have. And there are 3 different shapes or forms of clouds that you should know.
They're either puffy, fun, cumulus clouds like the ones we all draw, flat, sky-covering sheet-like stratus clouds, or way up high, wispy cirrus clouds. After you've figured out their form, the next thing you need to look at is how high in the sky they are and if they're raining. A puffy cumulus cloud that's raining is then called cumulonimbus, and then the stratus cloud that's raining is a nimbostratus. Then you take a cumulus cloud and you move it higher, it becomes altocumulus, and even higher in the sky it's cirrocumulus. And then it's the same thing with the stratus clouds. And after that, the only thing you have left are the stratocumulus clouds. And can you see why they're called that?
And today's a perfect day for viewing clouds. Right behind me there, you got the cumulus clouds at a really low level. You've got the higher up altostratus clouds. And then if we go all the way around, you got cirrus clouds on the other side of the sky. Beautiful.
Now, do you need to know how to identify clouds? Absolutely not. But I kind of like using the terms stratocumulus and condensation nuclei. You should see if you could slip it into a conversation sometime. It makes you look really cool. Time to make clouds. So now it's time to make clouds in a bottle. The things that you need to make a cloud in a bottle, you need the bottles here, you need matches, and you need hot water. And that's really it, but you also need adult supervision because this can be a little bit dangerous with the hot water and the matches. All right, so the first thing that we need to do is we need to choose our bottle. So you guys pick a bottle that you want to use.
I choose this one.
Now, I went to the store and I got these bottles because they're plastic bottles and they're nice and strong. They're not flimsy ones. The stronger ones are easier to squeeze and they pop back from squeezing later on a lot better.
Like that.
Okay, next we need hot water. And I'm just gonna put a little bit into the bottom. You don't need a whole lot of hot water here.
Like about an inch, right?
Sure, maybe about an inch, that's about right, honey. So Sam, get a lid and put it on your hot water as soon as you can. We don't want that hot air escaping.
Exactly.
Good.
Now what if we put smoke in the bottle?
That's what we're doing next. So everybody have hot water?
Yep.
Now when you do have hot water in your bottle, you'll see on Natalie's it looks like it's kind of smoky already. That's just condensation on the inside. If you shake it up, you'll see that the bottle's actually clear. The next thing that we need is we need smoke to act as condensation nuclei. So I will once again be in charge of the smoke too. Sam,
Because he's actually like,
give me your bottle as soon as you're ready.
It actually says, there goes your bottle.
Oops.
On yours, Dad. Hot water.
And then lid back on your bottle as soon as you can. Ready?
Yeah, I'm keeping it. It freaks me out.
So now what we have is we have hot water inside these bottles, which is going to give us very, very humid air, 100% relative humidity, saturated air is full of water vapor. We put in condensation nuclei from the smoke. And the last thing we need to do is we need to cool the bottle off so that the clouds can form. The water vapor can condense onto the condensation nuclei and give us a cloud. So what we're gonna do is give it a shake, then you squeeze and release, and you have your cloud in a bottle. There it is. There it is, Sam. You squeeze, release, and you have your cloud. All right, bud. You guys ready to free your clouds? Go to the air, cloud. Goodbye, little buddy.
I think we're definitely helping the air.
I hope you enjoyed learning about clouds today. If you have any questions or comments, please leave them. And feel free to subscribe and like this video if you did, or if you didn't like it, I guess unlike it, and tell me why. Have a good day.
A person can go 3 weeks without food, 3 days without water, and 3 minutes without air. Watch this. Oh. Airball. Hey everybody, Dave Wookner here, Chief Curiosity Officer. Today's video is all about air. Because if air is so important, shouldn't we know everything there is to know about it? Let's start with the question, what exactly is air? If you said gas, that's right. If you said oxygen, that's 1/5 right.
And that's because here at the surface of the Earth, 78% of the air we breathe is nitrogen gas. Only 21% is oxygen.
Think about that. For every breath you take in, only part of what you're breathing is actually used by our body to live. The next question is, what is a gas? And why can't we see it?
The gases in the air are invisible because they're either a single atom of an element, the smallest building block of matter, or they're molecules, a combination of two or more atoms bonded together.
Either way, they're far too small to see, and they rarely interact with light. It's like seeing a single string from a mile away. You can't. But a million strings wound together?
Like the atoms in a solid or liquid?
That you can see just fine. And before I go on, it's time for the amazing science question of the day. Which terrestrial planet, one with a solid surface, has the thickest atmosphere? Stay tuned for the amazing answer. The next question is, why does Earth even have an atmosphere in the first place?
And it's because of the strong magnetic field from the molten outer core of the Earth and gravity. And can you guess why the moon has no air, no magnetic field, and a lot less gravity? And gravity pulling the air down also explains why there's less of it as you go up.
Now let's check out the following graph, and that includes you adults, because this graph answers a lot of questions.
Like, why do airplanes carry oxygen masks? Well, if they lose cabin pressure, they're flying at 30,000 feet or higher. And at that elevation, they only have about 30% the air of a person at sea level.
Now pause the video, Google your elevation above sea level, and find out how much air you have where you live. And if you feel like it, leave it in the comments. Now we answer, why is air so important? You know we need food for energy to live, right? But there's another thing we need to get that energy out of the food. It's oxygen. Now our cells take sugar from food, they take oxygen from air. You put them together, boom! Energy is released and powers us in our lives. Then after that reaction, the sugar and oxygen become water and carbon dioxide. Basically, that's how you lose weight. It's by breathing out CO2 and then getting rid of that water any way possible. We won't go into details. Wait, but if this is true, aren't you destroying precious oxygen every time you breathe in? Shame on you.
Actually, no, because that CO2 is then grabbed by green plants and used in photosynthesis to create sugars and oxygen that we breathe and consume. It's a cycle. We need plants and they need us too.
And now it's time to answer the amazing science question of the day. And the answer is Venus. Venus has an atmosphere 90 times thicker than that of Earth's. It's enough to crush anything we send there. And its temperature is 530 degrees hotter than Mercury's, even though it's twice as far away from the sun. And that's because it has an atmosphere of carbon dioxide gas, a greenhouse gas that absorbs heat energy and holds it in. And did I mention it rains sulfuric acid?
So air is important wherever you are. I hope you now have a greater appreciation for the air we breathe. If you enjoyed this video, please like and subscribe. I need to get into better shape.
How is it that hot air balloons go up? And how do they get back down? And what else rises and falls on Earth? The science of convection is responsible for a great many things we experience and see here on Earth. From earthquakes to volcanoes, mountains to canyons, climate, storms, and even sunshine. This is convection. No, wait. That sounds so boring. This is the super awesome, matter-moving extravaganza of science. And if you think of something even better, leave it in the comments below. Smoke rises, right? Well, not exactly. Hot air rises. Smoke just kind of hitches a ride.
But why does it rise, Dad?
And that's a good question that we'll get to later. But first, let's talk about what else rises and falls on Earth.
Starting with air. Now, warm air rises away from the warm Earth's surface, but then it cools by releasing that heat.
The cool air sinks back down, rushing in to replace the warm air that rose up. That's what gives us wind. It's also the answer to how hot air balloons come down. They need to become cold air balloons, or at least normal air balloons, and then their weight will bring them down.
This happens on a global level too, giving us winds that blow things across the planet like storms and ships.
This is classic convection, and this is one method by which heat transfers or moves from one place to another.
Water in the oceans also undergoes convection, where cooler water sinks and warmer water rises to fill in the space. And I say cooler and warmer because it's really all relative. 50-degree water is cold, but it's a lot warmer than 40-degree water and will therefore rise.
Now, ocean currents are a little bit more complicated because there's more than just temperature that affects their motion, but they play a vital role in moving heat from one place to another on the planet, keeping us at a nice habitable temperature.
And surprisingly, the Earth itself undergoes convection, as hot mantle rock heated by the core slowly rises to the surface, cools, spreads out, and sinks back down. It's the driving force behind plate tectonics and is responsible for a large amount of what we see on the surface of the Earth.
We get that hot stuff rises, and we get that cold stuff sinks. But you still haven't answered why.
Alright, here we go. Now take these two rocks. They're roughly the same size, but one is much heavier than the other. Because it is more dense, it has more atoms taking up the same space as the less dense rock. The first rock is 28 grams. The second rock, it's only 11 grams, even though they're the same size. And watch as I drop these two rocks into a tank of water. The one more dense than water sinks, while the one less dense than water floats back up to the top.
As with all matter, solids, liquids, and gases, there are warmer areas and there are cooler areas. And as gravity pulls those cooler areas down, they'll go under and push up the warmer, less dense areas. It even happens in the sun. What you're seeing here is the very top of these convection cells that are bringing hot plasma from near the core of the sun up to the surface where it radiates out its light energy.
Now, as you can see, convection plays a key role in the movement of matter throughout the universe. But there's just one more thing that I wanted to try, and it was making a hot air balloon at home with my kids. Now, to make a hot air balloon at home, you need a heat source, so please make sure that you only do this with adult supervision. And we tried out a couple different types of trash bags to see which one would work the best. It turns out that the cheapest, lightest trash bag you could find at the grocery store was often the best one. We also tried the grocery bag that you put produce in, and that one worked fine too, but it was a little bit harder to capture the air in it, and they melt pretty easily. Now, as you can see, bags alone work, but we decided to make it a little bit more interesting by building our own little basket with our own little passenger. Now, this was a little bit more complicated and it was a little frustrating, but as you'll see in just a second, it works too, and it's actually pretty cool. The real key to success was just finding a time when the wind wasn't blowing and the heat was rising straight up from the source.
Now, I could spend all day telling you examples of convection, but instead, with your newfound knowledge, I'd like you to find examples for yourself. And feel free to share them in the comments below. I hope you have an uplifting day. Bye.